Well, hi there, boys and girls. Today we're going to try and deepen our understanding of the difference between continuity and differentiability, if there is one, depending on which way you look at it, and also the different forms of the derivative and what they say once you calculate a derivative. So let's get started with, I guess, the difference between continuity and differentiability. Continuity only requires, when you do this, that we've got to have the limit as x approaches a of f of x has to equal f of a, and on top of that, both of these must be defined. In other words, f of a has to exist and the limit has to exist. Alright, now as a working knowledge, we just need this to mean when we're looking at the graph, are there no gaps or holes? I cannot have any gaps or holes for continuity. So when I'm looking at a pretty picture, I'm just going to scan my eyes through here and say, hey, are there any gaps or holes in the graph? And if there are gaps or holes, then I have to exclude that from being continuous. So we're going to list the x values for which the function appears to be not continuous. We're going to do that first. So I'm going to answer A. So as we scan through this little graph, I could draw all of this with my pen or pencil without lifting. No gaps, no holes yet. No gaps, no holes yet. No gaps, no holes yet. Oh my gosh, here we go. We've got a gap. We've got a jump discontinuity here at 6. Therefore, I'm going to say x equals 6 is a place where the function appears to be not continuous. You keep going after that, I can draw it without any gaps or holes and we're fine. Now, not differentiable continues on that. Not differentiable. For a function to be not differentiable, it would have to be discontinuous, but there's other things you would have to look for. We would have to look for, does the graph have any sharp turns or cusps? Sharp turns, or does it have any vertical tangent lines? And in my opinion, that's harder. It's not necessarily harder to see, but I seem to miss those sometimes when I'm looking at a graph. So for differentiability, I've got to look for some extra things. Now, first of all, it has to be continuous. So I'm going to check for discontinuities, but then I've got to add places to that even though it's continuous, it still might not be differentiable. So let's take a look here. First of all, I'm going to say x equals 6 is a place where it's not differentiable. Why? Because at 6 it's not continuous. And if it's not continuous, we can't take the derivative. But there's some other places where I'm going to encounter some problems on this graph. And that happens right here at 3. From the left, my slope is negative, but immediately my slope turns positive. That is a sharp turn. Those slopes don't match. So I'm going to include 3 in my list here. Then this is the one that I sometimes miss. We go through here and I'm just thinking, oh, that's cool, hey, look, oh, but wait, right here at 4, it appears that the graph goes vertical for just a second. That would be a vertical tangent line. And what's the slope of this line? That slope is undefined. Derivative means slope, so an undefined derivative would make it not differentiable. So I have to include 4 in my answer for B. Also, I've already included 6, so we're fine there. That doesn't really look like a sharp turn to me. That's supposed to be maybe a flat. So we're scrolling through here, and right here at 8, I've got a sharp turn. So I'm also going to include 8. So that would be the places where it's not differentiable. It's not continuous at 6, sharp turn at 3, vertical tangent at 4, cusp or sharp turn at 8. So there's really more of a requirement to be differentiable. But I am going to say something that you will know for sure. If you know a graph is differentiable or differentiability, this is going to imply something. If you know a graph is differentiable, then you already know that it is continuous. So differentiability implies continuity. Say that 5 times fast. All right, let's take a look at making sure you understand positive slopes, zero slopes, and negative slopes. In this next example, at which labeled points is the slope of the graph 0, positive, or negative? So a slope to be 0, I need to have a horizontal tangent line. So I need to have a horizontal tangent line. So let's take a look at the graph. As my pen goes through here, right here I have negative slopes, but right here at B, a tangent line at B sure looks like it would be horizontal. And then also up here at E. Something neat about this that we're going to look at with applications of derivatives, when the slope is 0, we know we have minimums or maximums. That's how we're going to find mins and maxes. We're going to find the derivative where it's equal to 0. But for now, the question is just, where does it look like we have a slope of 0? And it looks like to me at B and at E. That's going to happen at maximums or minimums on a graph, as long as it's a smooth curve anyway. Otherwise, the derivative would be undefined. So I'm going to say B and E here. Now, what about a positive slope? A positive slope means the graph has to be increasing. And I've got negative slopes here, but on the right side of B, out here at C, I've got positive slopes at C. I've got to also still have positive slopes at D. But after that, E is 0 and F would be negative. And so the other two answers for negative slopes here at A and also negative slopes there at F. So I hope that makes sense to you. If not, come talk to me and I'll show you the little moving tangent line on my computer. So A and F are my answers to that. So now hopefully that helped you out with differentiability and continuity. Now we're going to take a look at some different forms of the definition of the derivative. And there are 3 that you must know. I'm going to go ahead and write them down. First of all, f prime of x is equal to, I better put the limit as h approaches 0 first, f of x plus h minus f of x all over h. You saw this last year in pre-cal, you saw it again this year. That's the traditional way of finding the derivative for a function. There's also 2 ways of finding the derivative at a point. I'm going to say f prime at c. F prime at c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. This was our alternative definition of the derivative. There's also one more, and that is that f prime of c can be found using this formula but plugging in c for x immediately. And that would be the limit as h approaches 0 of f of c plus h minus f of c all over h. It's very similar to this one, but the x has been replaced with c. So let's look at this example. Let f be a function which satisfies f of 2 plus h minus f of 2 equals all of this. This almost looks like a difference quotient, but I don't have a division. So it's almost a difference quotient. For all real numbers h, find f prime of 2. So I'm going to set up f prime of 2 using one of these 3 definitions. Let's take a look at what they have given me. They've given me this. Now, that really doesn't look like anything over here, so I'm not going to use this second alternative definition of the derivative. It sort of looks like this first one, but that 2 should have been an x for me to use the first one. What it looks like mostly to me is this third definition. It looks like this. And so f prime of 2 would equal the limit as h approaches 0 of f of 2 plus h, plugging in 2 for my c, minus f of 2 all over h. That would give me the value f prime of 2 if I were able to do all of this. This is an AP-like question. Well, can I do this top part? I don't really have a function to plug it into, but they do tell me that all of this numerator right here, f of 2 plus h minus f of 2, is equal to this. So I guess they've done the algebra for us. So that means that they were nice, although it was a little harder to figure out how to set this up. So I'm going to replace this entire numerator with 5h minus 3h squared plus 9h cubed. So this becomes the limit as h approaches 0, I'm going to say f prime of 2 equals this, of, and I've already forgot what that said, that is 5h minus 3h squared plus 9h cubed. And that's this entire numerator. But I still have to divide by what? Did I hear it out there? It's just like Blue's Clues. That's right. I heard it. Good job. Divided by h. Okay, so now we just have some algebra to do, because if we plug in 0, we're going to get 0 over 0. So I'm going to factor an h out of the top, which will leave me with 5 minus 3h plus 9h squared, all divided by h. Looky here, I'm happy, happy, happy. Those h's are gone, and now I can plug in 0 for my h, and I will get, my screen just went a little darker because it's running out of battery. It's trying to conserve some battery, so if you saw that, you're not crazy. So if I plug in 0 for h, I'm going to get 5. That is f prime at 2. That's an AP question that sort of checks your knowledge of this definition. They don't give you the function, but you are forced to go through this definition of the derivative to figure out what the derivative is. Because a lot of us want to say, well, I just want to learn the shortcut for derivatives, and I don't ever want to learn these three. Unfortunately, the AP test forces us to know those definitions, and that's a good thing. All right, so let's do another one that's an AP question, and it says we've got f has a function that satisfies this property right here for all real numbers x and y. That means this y could be an h, or it could be an r, or whatever, and this is always true no matter what you plug in, as long as x and y are real numbers. And they also give me this little weird statement that if we have this situation that works out to be 2, use the definition of the derivative to find f prime of x. They're sort of forcing my hand here because there's only one of these that we have. There's only one formula for f prime of just x, and that formula is the limit as h approaches 0 of f of x plus h minus f of x all over h. That's the only one I really can use. So how can I use this information that they gave me up here, which looks pretty difficult? How can I use that to answer this? Do you know that f of x plus y is exactly equal to f of x plus h? If I can plug h in for y because it says it's true for all real numbers. So this is sort of a weird way of me substituting, but y is just a dummy variable anyway. So f of x plus h would be equal to f of x minus 4 times not f of y, but 4 f of h, and then plus 9xh. So that gives me a formula for my f of x plus h, but I still have to subtract off f of x and divide by h. So let's see how that looks. The limit as h approaches 0 of, I'm going to do f of x plus h first, f of x minus 4f of h plus 9xh. Using this formula that they gave me, I've calculated f of x plus h. I still have to do minus f of x, and this is all divided by h. Now at this point, we have to do some algebra. We'll notice that f of x here, which I don't even know what that is, cancels with this f of x here. And I get the limit as h approaches 0 of negative 4 f of h plus 9xh all over h. Now this is even a more tricky AP-like question because I can't really factor an h out of f of h. So what can I do? I can do something that I learned about limits, and I can separate this into two fractions. Just remember that a plus b over c is equal to a over c plus b over c. That is a true statement all the time, unless c is 0, of course, but that would be silly. So I'm going to separate this into two different fractions. I'm going to have the limit as h approaches 0 of negative 4 f of h over h, and then plus the limit as h approaches 0 of 9xh over h. So I just separated those two. So let's see if we can answer these. F of h over h as h approaches 0 is given to me in the problem. So the answer to this one would be negative 4 times 2. I've replaced this, the limit as h approaches 0, because they told me this, with 2. And then on the second one, of course, I can cancel those h's, and that is just 9x. So this is negative 8 plus 9x. That is f prime of x. Another way where the AP exam forces you to know. It's just good things. Some things you just have to memorize. We have to use these formulas even after we learn shortcuts. All right, so let's take a look at another AP question that completely checks your knowledge of what a limit statement says. Right now, I have a limit statement, and it says it's equal to 3. And which one of those 3 definitions of the derivative are we using? Well, of course, you should go back and see. It's the limit as x approaches a. Or actually, let's see if I use c. I want to use, it doesn't really matter, but I want to see if I used c. I did, so I'm going to go back and change that to a c. So be patient with me here. All right, change that back to a c. So we're using the limit as x approaches c of f of x minus f of c all over x minus c. And what does this equal? This equals f prime at c. So if you get an answer to this, you know that's the derivative at c. So this is a given. The limit as x approaches 5 of f of x minus f of 5 over x minus 5 is equal to 3. What does that say? What does that mean? Take a look at this over here. If you do all this and you get an answer, it tells you that the derivative for the function at this value is this number. So this statement right here should tell you that f prime at some place is equal to a number. So what's my value I'm looking at? Well, hopefully you can tell that that is 5. The derivative for f at 5 worked out to be 3. So we know the graph was at least increasing at that point. If you know that you took a derivative, what else do you know about the graph? If it was differentiable, if differentiation was possible, what else must you know about the graph? Let's take a look at this last statement. Well, not last statement, the previous statement. If you can take a derivative, the graph is for sure continuous. So I'm also going to add this over here, and I'm going to say that f of x is continuous when x is equal to 5. Otherwise, we couldn't have taken a derivative. So with all of that being said, let's check these. Are all of these must, might, or never? F prime of 5 is 3. That must be true. That's exactly what this says. F prime of 5 is 0. You cannot have two different slopes at the same x value, so this is impossible. Now what about f of 5? What is f of 5? F of 5 is the y value. Does the derivative say anything about the y value? Well, it does in here. It will tell you the y value, but you would need to know what f of x was to figure that out. But do we care about the y value when we're looking at slopes? The y value could be anything, but the slope just depends on the curvature of the graph. So I'm going to say here that this might be true, but it doesn't have to be true. Part D, f is continuous at x equals 0. Well, this statement said it was continuous, but only when x equals 5. We took the derivative at 5, so therefore f is continuous at 5. Could f be discontinuous at 0? Does this statement say anything about f at 0? No, it doesn't say a thing about that. So this might be true. What about E? F is continuous at 5. Well, folks, we took a derivative and we got an answer. We took a derivative at 5. We got an answer of 3. Differentiability implies continuity. This must be true. And this last one checks your definition of continuity. For a function to be continuous, the limit must match the function value. This is for sure the definition of continuity, so that must be true. So tomorrow in class, you're going to work on a worksheet to really try and solidify what a derivative means, the difference between differentiation and continuity, and really how they're connected as well. And I will see you guys then.